All right, so today we're gonna prove the Riemann theorem. Okay. So let me state the theorem. So the theorem says if this Fz is analytic and bounded, in a punctured neighborhood, d prime 0r. So we use this notation for the punctured disk. Center at 0 with radius r. Okay, so 0 is excluded from there. Of an isolated singular point so notice that this F may not be analytic at this point. Then the singularity at A is removable. So removable singularity means that the Riemann series expansion, all the singular part of the Riemann series expansion vanishes. Okay. All right, so let's prove this. All right, so since this Fz is bounded in a punctured neighborhood, so that i.e. we have this modulus of Fz is less than n. All right, and then so we want to show, basically what we want is that we want to show that the singular parts disappear, right? So yeah, so let's write out the singular part for the Riemann series expansion. So that k any positive integer. Yeah. So here we will use a small trick to present the Riemann series singular part of the Riemann series expansion. So then we have, okay, so memorize remember that so the formula for the Lorentz expansion is, so let's recall that. Yeah, so I need to recall. Yeah, so so let's recall. So the formula is, so where AK is equal to 1 over T and I line integral over okay. So yeah, I'll use this notation gamma for so if a function is defined on a neighborhood omega, and then yeah, so this is like a general definition, right? So this gamma is arbitrary, simple, closed, positively oriented. Curve with finite length. Yeah, so let me check whether the term rectifiable is it means finite. Okay. All right. So let's just say that this gamma is a simple closed rectifiable arc. Okay. Where yeah, you can say just arc is like a arc is like a parameterized curve or something. Okay. Yeah. Okay. So here this gamma. So yeah, I think it has finite length, and then yeah, sorry, yeah, I'm a little bit unsure here. So yeah. Okay, I'll calculate later if I have. Just think of this gamma as a simple closed curve. Okay. So what's that? So so then what we have is, oops, where is that? Okay. Okay, so this is the Lorentz expansion of this F. Okay. think this should be f of zeta. So I feel like there's a typo for this one. Okay. Yeah, I think there's a typo. Okay. Anyway, so just temporarily take this as a definition. Okay. So here what we do is that if k is negative, right? So what we want is that we take so okay. So in this case, if k is negative, then so this is like yeah. So this is so like so this is like so you can think of this as -1 power, right? Yeah. And then so if k is if k is if this k is negative, then this negative k is like the absolute value of k, right? It's actually the positive part of the k, right? So and then this is negative. So like so we will switch it, right? So we switch it. So think of the so think of like e to the this one is equal to 1 over 2 pi I integral gamma f of zeta times zeta minus a to the yeah, so this k is the positive part, right? And then okay, so this zeta since it could be any arc inside the domain omega, so we pick it to be the boundary of the this center at 0 with radius rho. Okay, so we can do that. Yeah, and yeah. So pretending that the definition for gamma is true of what I said. Okay. So okay, so this rho is between 0 and r. Okay, the radius. Okay, so now what we have is that we have the modulus of this one is less than equal to assume that so y okay, so assume that this is true. So it's less than equal to 1 over 2 pi. So this is wait. Hang on. What I'm saying. So okay, so since M is bounded by the big M, right? So this is bounded by big M. And then this guy is bounded by what? This guy is bounded by yeah, so this one is bounded by rho, right? So this one is actually rho if you take the modulus, right? Wait. Okay, sorry, it's centered at A, right? Yeah. Okay. And then yeah, so this is less than equal to 1 over 2 pi times m. This is like rho to the k minus 1 power times 2 pi rho, which is the whole circle. and then this is equal to okay, so this is like cancelled out here, m times rho to the kth power. Okay, so so for any k it's true, right? So for any k, okay. So okay, yeah, because this rho is arbitrary, right? So it's satisfied for any rho between 0 and r. So basically, rho is arbitrary. So this implies that because this number is non-negative, right? And then it's less than or equal to this whatever m times rho to the kth power for whatever rho. So in this case, it must be equal to 0. Okay. So since k is arbitrary, so we have that okay, so therefore all the singular part vanishes. Alright, so yeah, the proof ends.